even sure. I didn't even know it.
All right, so we're taking a limit here. Look at this up here. Now I know what's troubling on this one. What's troubling on this one is that you've got x's and delta x's in there, right? And you're used to taking limits as x approaches something, right? Okay, this is different though. This limit here that we're looking at, they want us to find the limit as delta x approaches 0. Okay, so is x a variable?
Yes.
It is. Is x a variable of the limit? No, it is not. The variable of the limit is, oops, I gotta get my pen, is delta x, yes. Okay, so, right? Delta x is the variable that is approaching a value, and so insofar as the limit is concerned, x is a constant, right? X is not changing. Delta x is changing, right? So then, if we let delta x approach 0, we get 0 over 0, right? What do you suppose, this really isn't a very hard one though. What are we going to do to this limit algebraically to simplify it? Yeah, we're just going to, right, we're going to expand out the binomial x plus delta x squared, right? Okay, and then distribute the 5, and when you do that, you can already kind of look ahead a little bit here, right? When you do that, you're going to get 5x squared plus some other stuff, right? But look what's going to happen, 5x squared minus 5x squared. So we call those the naked terms, right? The terms that don't have a delta x in them are all going to cancel. Okay, and then you take it from there. Okay. All right, so there's one.
So you would separate it out to have like the x plus delta x times x plus delta x, or would you just?
Well, okay. I'll tell you what. Let's do a quick. Maybe that's a good thing to do for today's kind of a weird day. First day back. Do you remember how to do binomial expansions? Okay, how were you guys taught to do binomial expansions?
You know, because you square the second and the first term.
Okay, but what's like? What if we had a plus b to the 4th? Do you know how to get that quickly? There is a formula for the binomial expansion, but nobody ever remembers it. It's one of those things that have to be a Google thing, right? I mean, you'd remember if you use it a little bit, but it's not something that you use a lot. There is a really quick and easy way, though, to come up with moderately sized binomial expansions. I'm going to show that to you. This is good stuff. This is an audible. We weren't planning this today, but I didn't like the look of the D, so we're going to try something a little different here. Okay, binomial expansions. And so our goal is to be able to do something like this, for example. A plus b to the 5th equals what? So that's our goal. Here's how we can do this. The vehicle for doing this quickly is something called Pascal's Triangle. Remember that? From last year, you remember Pascal's Triangle? Well, Pascal's Triangle is huge.
Was that where you had like the sub numbers? No.
Pascal's Triangle is just this. The way you build Pascal's Triangle is you're going to start with a 1, and then you get a 1 and a 1. Okay? And the way you do this, then, every row we're going to add 1 digit to the row, and the way that you get those digits is by adding up the digits above to the left and the right. So for example, this next row, I've always got 1s on the outside, all the way down the triangle.
Oh, yeah.
But the one in the middle, 1 plus 1 is 2. Okay, so the next row would be 1,
2,
3, because 1 plus 2 is 3, 2 plus 1 is 3, right? See what I'm saying? Okay, you can already see that you're going to build a symmetrical. You're going to get symmetrical rows of numbers, aren't you? Right? Because everybody sees that, right? So the next one's going to be 1,
4, 6, 4, 1.
Okay, we'll just go one more. What's the next one?
5, 10, 5.
Good. Okay, what are those? Those are the coefficients of a binomial expansion. Okay? all we have to do then, so for example, if we want to know what a plus b to the, and it could be x plus, it could be anything, right? But we're doing a binomial, just a is the first term in the binomial and b is the second term, right? So a plus b to the fourth, all we'd have to do is just count down which row that is starting at 0. So this is the 0th row. This is the first row, second, third, fourth, etc. Okay? Oops. Second should be there. Kind of got those. Let me go back. Kind of got those off a little bit, didn't I? 1, 2, 3, 4, 5. So if we're doing, let's say, a plus b to the fourth, this is the row that we're going to use. Okay? So then what's that tell us? It tells us that a plus b quantity to the fourth is equal to those coefficients times powers of a and b that we'll discuss how we get the powers in a second. It's really easy. So these coefficients pop down. So we get 1, 4, 6, 4, and 1. And what goes here? Well, the sum of the powers of a and b has to be what? 4. Has to be 4, right? When I expand this out. So I'm going to start with all of the weight shifted to we'll make it the first. That's usually how it's written. The first term, and completely shifted to the first term. So I've got a to the fourth, b to the 0, plus 4, what's going to happen next to the powers? Yeah, they have to add to 4 always, but now the a's are incrementally decreased by 1 as the b's incrementally increased by 1. The sum of the exponents always being 4, because it's the fourth row.
It would always be addition.
It'll always be addition, but a or b could be negative. And so really a lot of books will show a separate binomial expansion for a minus, but you don't ever need it. All you need is just the plus sign, but b could be a negative number. Okay? We'll do one example like that. So then this is going to be 4a to the 3, b to the 1, plus 6, a squared, b squared, plus 4, plus 1, a to the 0. Okay, but some of that's unnecessary. What's anything to the 0 power? 1, right? Anything to the 1 power is just itself, right? And so we could have simplified that a little bit, couldn't we? Right? We could have written that as, we could have just written this as a to the fourth plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth, right? It shouldn't make any difference though, and I want you just to see, I know you will see this, probably already do, but addition is commutative and associative, right? So it shouldn't make any difference the order in which I add the a and the b, right? Therefore, do you see that the a and the b are completely interchangeable and symmetrical here, right? Does that make sense? Notice that I get 4s with the terms that have one of the 2 cubed and the other one of the first power. They're both 4s, right? Notice that the only oddball one in the middle is the one that has both a squared and b squared. So once again, if I interchange everything, it looks identical, right? And it has to. There's no preference for a over b. They're interchangeable. Make sense? Okay? So then we could quickly, by just slapping down this Pascal's triangle, we could expand anything pretty easily. Like let's just say, for example, we want to expand do this one. Expand x minus 2 to the 5th. Using a Pascal's triangle. there's 0, 1, 2, 3, 4, 5, right? That's easy enough, right? And now we're essentially done. What do we get for our answer? What's our A in this case? A is X. Okay, Jonathan, what's our B? Negative 2. Good. So we're just going to get 1A to the 5th, right? Plus 5 X to the 4th, what to the 1? Negative 2, right? Plus 10X cubed, negative 2 to the 2, right? Okay. Plus 10x squared, negative 2 cubed, plus 5x to the 1, negative 2 to the 4th, plus negative 2 to the 5th. Of course, negative numbers to odd powers are negative, right? So I could simplify this to just be x to the 5th plus, what am I going to get, negative 10x to the 4th. Do you see that? Oops. So I can just make that a minus. Right? That's going to give me a positive 4, so plus 40 x cubed, right? That's going to give me a negative 8, so I'm going to get minus 80 x squared. That's going to give me a positive 16, so I'm going to get, what, 80 again? And then this is going to give me a 32, right? See how easy?
Wait, what was 16 times 10 to the 80?
Did I mess it up?
Oh, no, never mind. That was
Okay.
my bad.
Wait,
Which one you get? Which one are you questioning? This one?
oh, yeah.
No, I thought you said negative 2 to the 4th, so I was thinking
Oh, okay.
16. So.
All right, does that make sense? Okay, there's our quick Pascal's triangle tutorial. So that's a good little trick. Later on in the class, we'll talk about ways we can actually remember maybe the binomial theorem, but this is a pretty quick and easy way. Obviously, if you had huge expansions, like if you're to the 12th power or the 20th power, you don't probably want to make a Pascal's triangle. Then you just use the binomial expansion formula. Okay, and I don't want to do it today, but there are ways that we could predict what these digits are going to be based on the row that we're talking about, right? The power of the binomial expansion. Okay? All right, so whoops, where were we? We were back. Oh, never mind. We were back here. Okay? And so, well, never mind. That works. 7, right? Yeah. Yikes. Okay, what's our trick for this one? We had a strategy, and it's called a rationalizing technique. Okay, the problem here being, I get 0 over 0, right? But the big problem being that I'm getting a 0 on the top that's part of an expression that involves a square root. Okay? What I would really like to have happen is I would like to have none of the offending factors, we call them, none of the factors that go to 0 involving a square root. Okay? So what was our trick? The conjugate. Good. We're going to multiply top and bottom by the conjugate of the expression that goes to 0 and involves a radical. Right? So we're going to do something like this then. We're going to get the limit of 13 minus radical x over x minus 169. times 13 plus radical x over 13 plus radical x, right? As x approaches 169. What's the benefit? What do we get on top?
You get rid of the square roots.
Yeah, because now this is a conjugate product, right? So we're going to get a difference of squares. Everybody agree?
So
A plus b times a minus b is a squared minus b squared. Okay. So I'm going to get 169 minus x on the top, right? Everybody agree? Okay, what about the bottom? Well, on the bottom, I've got those two factors being multiplied together, right? So I've got x minus 169 times 13 plus radical x. Okay. I don't quite have the cancellation I need. What do I have to do first? Well, I can't just arbitrarily multiply by -1. I could multiply top and bottom by -1. But I think what you mean, instead of multiply by -1, you mean what? Say it again. Factor out a negative out of the top, maybe, right? Might as well put the negative in the top. That's good form, right? So then that's going to give us what on the top? If I factor out a -1, what am I getting? Minus 169 plus x, or x minus 169. Put the positive term first. So I get negative the quantity x minus 169 over x minus 169 times x, 13 plus the square root of x. Right, as x approaches 169. Well, there we go. There's the whole, isn't it? Right? The whole is caused, and the function is caused by these two factors, right? That cancel algebraically. That's my 0 over 0 indeterminate behavior. Algebraically, I can cancel those, and then I'm left with the limit of -1 on the top, right? Over 13 plus the square root of x on the bottom. Well, I can take the limit. As x goes to 169, what do I get? What's the square root of 169? 13, right? So if I take this limit, don't I just get -1 over 26?
Is there a pattern to those? Because that's the third one you've done that's like that. That's the third time when the answer was the top number doubled over 1 with the change in sign.
Yeah, okay, because they've all, yeah. I mean, the answer is yes
Is it
and
a
no.
coincidence? Or
I mean, it's, here's my best answer to that. My best answer to that is when we know how to do,
Is there a pattern? That's all I'm asking.
there is, but you want to be careful with trying to determine if they're patterns, because the pattern, I could make a problem like that where it didn't work out so nice.
But you wouldn't do that.
Oh, I might. I'm a pretty mean guy. I might. You never know. Okay, so there's your question. Now, what I want to do today is I want to show you something cool, really cool. No.
Zoom in, zoom out. So I'd be okay with that.
Okay, so what I want to do is I want to show you how to deal with some other kinds of problems. Like, for example, I'm just going to pull it up here. Let's say, how do we deal with something like this? Been a while. Whenever we're faced with a limit, what do we always try to do first? Yeah, evaluate directly, right? And what are the two cases where we're done? If if I try to evaluate something directly, what's one thing that could happen where we get an answer and we're done?
If you get a number over zero.
Okay, one thing would be if I get a number over zero. That's kind of usually our second, our second look that we could get. What is, for now, what is our answer to that? No limit. Yeah, we can't, right, you can't divide a number by zero. That is no limit. Okay, later on we'll be more descriptive, but for now that's no limit, we're done. What's the other thing, even easier, that could happen? Yeah, I just get some fraction, right? Some fraction that has a real number value, has a rational number value, right? So I'm gonna get some number divided by some number, okay? Or this could happen. What happens here? Well, okay, but what do if I try to evaluate directly, what do I get? 0 over 0, which is indeterminate, which just means more work, right? But what's our more work look like? In this case, we don't have, none of those strategies we previously used are going to be effective.
Do you use one higher?
Well,
Like multiply both side, or like top and bottom by 10, and then you get 10 squared, maybe do something, like, I don't know.
Okay.
Off the top of my head. But, like, maybe convert 10 into whatever sign squared minus 1 or something.
well, those are good ideas. They're not going to pan out easily.
They're not.
Here's what's going to help. I withheld some information though. Here's what's going to be helpful to you. There are two indeterminate forms, trig forms, for which we know answers. And I'm going to prove one of those. I'd like to today. I don't know if I have enough time. I really want to. This is so cool. 11:43. No, I'm not going to. I'll do that tomorrow. But at least I'll show you how this works. The thing I'm going to show you tomorrow has nothing to do with the assignment. It's just a cool proof, different kind of proof than you've probably ever seen. So you'll like it. It's good. But the way we do this is we just take advantage of these two indeterminate forms for trig limits. One of them is the limit of sine theta over theta as theta approaches 0 is, any guesses? It's 1. I'll prove it to you tomorrow. Okay, that's the one we use the vast majority of the time, and these are found, if you want to see these again, they're on page, two special trig limits on page 62 in your textbook.
Wait, so
So that's
you're
one.
getting to the proof?
Yeah.
Okay.
No, I'm not going to do the proof today. I'm just going to use this today. Tomorrow I'll show you the proof one
Okay.
more time. So the other one is the limit of 1 minus cosine theta over theta as theta approaches 0 is 0. So those are two, and this one needs no proof because, as I'll show you tomorrow, if I can prove this one, I can use trig identities and easily get from here to here. Okay? So they're both, this one takes care of both. For today, let's just look at how these are useful. Tomorrow I'll prove it. So now, given that, what do you think we can do with this? Any suggestions?
Can you change the tangent, because you know the tangent is sine over cosine?
Okay, good. And that's always a good first step. Whenever you're given a compound trig function, a trig function that's built from sines and cosines, you always can just write it in terms of sines and cosines. Okay? So we're going to rewrite this as the limit of sine x over x cosine x. Everybody agree? Everybody agree? Okay. Now we can group this, right? We can group this any way we want to. I can write this, it's written as one big product slash quotient here, right? But could I write this as a product of two quotients instead? How could I conveniently split this up?
Sine x over x.
Ah, okay, good. I could write this as the limit of sine x over x times 1 over cosine x as x approaches 0. Now we go back to those properties of limits. What did we say earlier about the limit of a product? So we said something like this: if the limit of f of x as x approaches c is L, something like this, the limit of g of x as x approaches c is K or something, I don't remember what it was, right? then what is the limit of f of x times g of x as x approaches c? Okay, right? In other words, I split this into a product of separate limits. We don't have to show that work, right? It's probably not necessary. But technically, we wrote this as the limit of f of x as x approaches c times the limit of g of x as x approaches c. But I just know that I can evaluate the limit factor by factor. Okay? So it's just LK. So how does that help us here?
Sin x over x.
Ah, that's one of our special limits, right? The limit of sine theta over theta as theta approaches 0 is 1. Well, replace the thetas with x's, right? So this one goes to 1. What does this one do? As x approaches 0, what does cosine x approach?
Probably.
Think unit circle. Cosine's the x component, right? So that's right here, right? That's 0. That's an angle of 0. So cosine's the x coordinate, that must be 1, right? So this gives me 1 over 1. 1 times 1 over 1 is 1. Make sense? Right? Okay. So how about, time for one more. How about one like this? What if we want to take the limit of sine 5x over x as x approaches 0? I can't do that.
Aren't they two different things because 5x is a x?
They are. They're different arguments. Yeah, the x doesn't go with the 5x, right? That doesn't match our form, right? If I write our special trig limit up here, the limit of sine theta over theta as theta approaches 0 equals 1. Well then, look, the theta appears 3 times. It has to be the same argument each time in order to match that
Well,
pattern.
Okay, but if x is approaching 0, then we put in 0. 5 times 0 is still 0.
Okay, so that's very good.
Still 1.
So one thing we can do is we could say, as x approaches 0, what does 5x approach?
0.
0. I get a freebie. I can put a 5 there. That's free, because that has to be true. But I still need a 5 there, so what can I do algebraically?
Wait, why would you need a 5 there?
Because that and that have to be the same in my limit, right? The argument of the sine function has to be the same as the factor in the
But
denominator.
5x is equal to x.
No, it's not.
In this
No,
case,
no, no.
where x equals 0,
Yeah, okay.
when 5x...
But they're not equal, and you're going to see that we're going to get a different answer than you expect, because you expect the answer to be 1.
Yeah.
Okay, it's not.
I'm just...
But there's a really easy algebra step. What are essentially the only 2 things I can do to a function to not change its identity? Okay, multiply by 1, in this case in the form of probably 5 over 5, right? Or I can add 0, which is rare. We almost never do that. No, it's fine.
Because then if
It's
you
fine.
separate it, it becomes
Oh,
5 times 1 is 5.
Ah, okay. See what we got here? So now look what we've got. Here's our theta, right? There's a theta, there's a theta, there's a theta, right? Everybody see that? So what this becomes then is just the limit. It becomes, I can pull the 5 out front, because it's a constant. I get 5 times the limit of sine theta over theta as theta approaches 0. Well, what's that limit equal to? Whoops. 1, right? So I get 5 times 1 equals 5. Right?
You crowd those wild.
Crowd goes wild.
It's just like...
Okay, make sense?
Yes.
Yeah, tricky. So you can kind of see that the last part of this section, this is a big section, evaluating limits analytically. There's a lot of work there. The last part of this is just doing stuff like this. It's taking trig functions, and if they're indeterminate, if the limit is indeterminate, you've got to use your trig magic. We get some trig practice here, which is good, to try to coax out one of those special trig limits, which removes the indeterminacy, right? Instead of canceling factors like we did before, Now we just know that the values of these limits are 1 and 0 respectively. Okay, so that removes the indeterminacy. Because these should be, I mean, they're both indeterminate, aren't they? This one is a 0 over 0 form, so is that one. But we know the answers. I'll prove it to you.